Hi GOH, this is Unit 4, Lesson 7, so this is the last lesson in this unit on constructions. We're going to inscribe regular polygons inside of circles, and those regular polygons are going to be equilateral triangles, hexagons, and squares. This is a popular question on the regions that has been asked several times, and it's pretty simple to do. So let's see, we're going to start with exercise 1. The directions are written there for us. But the first one we're going to do is we're going to do a square. So the way that you do that is you start off by drawing the diameter of the circle. It doesn't matter how you do it. I'm going to do it from left to right. And now you can just see that I missed that diameter, so I'm going to move my line down a little bit more. It's hard to judge when I'm doing it. Okay, so again, I draw the diameter of the circle. That's step 1, so go ahead and do that. And then what I do is I construct the perpendicular bisector of that line. So they said to call that line AB, so I will do that just because we're going to refer to those lines later on. All right, so I have line AB that I just drew, and I'm going to construct the perpendicular bisector of it. So that's my favorite one. Remember, all I do is I open my compass more than halfway, and you can see easily where halfway is because O is the center of the circle. And I draw an arc, okay, and then I go to the other point, point B, and I do the same thing with the same setting, okay, so I go to point B, and I draw a half a circle. Now where those two arcs meet at the top and the bottom, I'm going to connect them, so I'm going to get my ruler out, and I'm going to draw a line that goes through those 2 points. And that is the perpendicular bisector of AB. Now where that line touches the circle, not where the arcs meet, but you need to draw that line big enough so that it touches the circle. I'm going to call that point C at the top, and I'm going to call that point D at the bottom. Okay, so where the line, make sure the line is long enough that it touches the sides of the circle. And then I connect all those points. So I'm going to connect A to D. These are the sides of my square. My square is going to be kind of crooked. I'm going to connect B to D. I'm going to connect B to C. And I'm going to connect A to C. So polygon ACBD is a square. It's sideways square, but it's a square. Now, why does this work? We haven't talked about squares yet. We will. But basically, you're going to find out that the diagonals of a square are perpendicular and they bisect each other. So the diameter is one of the diagonals of the square, and then that perpendicular bisector is the other diagonal of the square. So again, the diagonals of a square are perpendicular and they bisect each other. So that's why those are the 4 vertices of the square. So they're going to sort of take us through a little bit. I mean, I said why right here. But they want us to understand the logic behind why ACBD in the last exercise must be a square. So we're going to look at the 4 triangles created in this diagram. So you can see there's a triangle in the top left, a triangle in the bottom left, a triangle in the top right, and a triangle in the bottom right. And they want to know why those triangles are congruent to each other and to explain why. Well, remember, this is a perpendicular bisector. So those sides are all going to be congruent to each other. But more importantly, AO, OC, OB, and OD are all the radiuses of that circle. And all the radiuses, we call that radii, have to be equal to each other no matter where you draw them. So all those sides are congruent to each other. And all these angles in the middle right here by O are all right angles because they're perpendicular. So basically, those triangles are congruent to each other by side angle side. AO is equal to OC is equal to OB is equal to OD because they're all the radii. And all the angles in the middle are right angles because we created a perpendicular bisector, so those lines in the middle are perpendicular. And since the triangles are congruent by side angle side, then all the hypotenuses, so that would be OC, BC, BD, and AD. All those hypotenuses have to be congruent by CP, CTC. So since the triangles are congruent, all the sides of those triangles, those corresponding parts, which in our case are the hypotenuses of those right triangles, are congruent. Those hypotenuses of the right triangle are actually my sides of the square. All right, now a square has 4 congruent sides, which we just showed, and it has 4 right angles. So why are those angles all right angles? Oh, that's part B right here. So basically, these are all isosceles right triangles. All of those 4 triangles up above are isosceles right triangles. So that means the measure of each of those acute angles would have to be 45 degrees. So each acute angle is 45 degrees. And then that makes angle ACD, CBD, BDA, and DAC. Just looking at my picture, I'm talking about the angles of the square right now. That makes all those angles of the square 90 because they are comprised of 2 45-degree angles. All right? But also what I said in the beginning, that the diagonals of a square are perpendicular bisectors, so therefore that is why that has to be a square as well. So on the next page, we are going to do an equilateral triangle and a hexagon. They are just as easy, a little similar, but a tiny bit different. So construction of a square is relatively easy. The construction of a regular hexagon, which is a 6-sided figure with equal side lengths and equal angles, and the construction of an equilateral triangle are tied together and are easy as well. First, let's see the relationship between the 2 figures. So I'm not going to use my compass up here. I'm going to use it down on the bottom. So let me just move that down. So A, B, C, D, E, F is a regular hexagon. Remember, anytime I put that word regular, that means all those sides are congruent. So I'm going to mark all these sides congruent. So AB is congruent to BC, is congruent to CD, is congruent to DE, is congruent to EF, is congruent to AF. It's a regular hexagon. I don't know if you guys can see, but ABC is a triangle. The triangle's sort of like in the corners. CDE is a triangle, and AFE is a triangle. And I want to know why those triangles are congruent to each other. All right, those triangles are congruent to each other by side, angle, side. Because in a regular hexagon, these angles also have to all be congruent to each other. All right, so each of these 3 triangles are congruent by side, angle, side. In a regular hexagon, all the sides are congruent and all the angles are congruent. So easy enough. So those triangles in the corner are congruent to each other. If those triangles are congruent to each other, then that means that AE would have to be equal to AC, would have to be equal to CE, because those are corresponding parts of those congruent triangles. So AE is equal to EC is equal to AC by CPCTC. So therefore, that triangle in the middle is equilateral. So I'm just showing you here, explaining the relationship between a hexagon and an equilateral triangle. If you take a hexagon and you connect every other point, so I'm connecting the A, I'm connecting the C, and I'm connecting the E, that triangle that you create in the middle will be an equilateral triangle. All right, so the hexagon and the equilateral triangle are the exact same construction. It's just a matter of which points you are connecting. For a hexagon, you connect all 6 points. For an equilateral triangle, you connect every other point. So here's how we do it. Same as before. I start off by drawing the diameter of my circle. Okay, and I will just adjust my line a little bit so it goes through the center. All right, so I start off by drawing the diameter of the circle. Now this one is a little bit different. I don't want to go past O. I'm not doing the perpendicular bisector. I want to go exactly into the middle. So I want the middle exactly. Okay, so make sure that your compass is on that end point right there, and it goes exactly into the middle. And you draw an arc. And then you go to the other side of your diameter, and you draw the same arc. So these 2 arcs, I'm just going to check right here that they are touching. They are exactly touching in the middle. They're not overlapping. There's not a gap. They're exactly meeting in the middle. Okay? And when I drew my diameter, they wanted me to label those points AD. And now I'm just going to, where the arcs are touching the circle, I'm going to call that B, C, D I already have, E, and F. So basically, where the two arcs meet at the top are points, where the two arcs meet at the bottom are points, and where the diameter of the circle was drawn are points. So if I want a hexagon, I connect every single point. So I could connect A to B, B to C, C to D. I know it's being a little bit messy at that C there. I'll go back and fix it. D to E, E to F, and A to F. Okay, that's my hexagon. If I wanted to, let's fix that a little bit. If I wanted an equilateral triangle, then I connect every other point. And I'll do that in a different color. So let me get a different color here. I'll do that in blue. So I would connect maybe like B to F and B to D. See how I'm skipping every other point? And D to F. So the blue one is an equilateral triangle and the black one was my hexagon. But both of those constructions are done the exact same way. You draw the diameter of the circle and then you go to the end point of the diameter and you go exactly to the middle and you draw an arc. And then you go to the other end point of the diameter and draw an arc. Those arcs meet in the middle, creating 4 more points of intersection on the circle. Okay, so using what we learned, we already did this part D already. Using what we learned in number 3, construct an equilateral triangle. State the name of my equilateral triangle. So you connect every other point, and that triangle would be triangle BDF.